All right. Ladies and gentlemen, we are currently recording. So, let's get started. All right. So, on Friday, we got ourselves into the next unit, and that next unit deals with forces and Newton's laws. So, last Wednesday into Friday, I had you guys fill out the outline that generally discusses forces. And we said that forces are responsible for doing what? What do forces do? Let's not say move objects. They cause them to change or accelerate. Forces are responsible for acceleration or changes in motion. Okay, forces are pushes or pulls, but what they end up doing is changing the motion of the object. So that means that forces are responsible for one of three things, or more than one of three things, right? Speeding up, slowing down, changing direction. All three of those being forms of acceleration. Okay, that's what forces do. Then we talked about Newton. We talked about how Newton. So we talked about Newton and how he comes to these realizations, and he comes up with three ideas that relate these how forces work and what they do, and et cetera, et cetera, et cetera. So on Friday, we talked about Newton's first law. We said that Newton's first law can pretty much get summed up with one word. What's that one word? Inertia. Okay?
Wait, is it? Oh no, what's the sleeping thing we just talked about?
So, first, inertia. Inertia is this idea that objects will continue doing whatever they are currently doing. And if that means that they're at rest, it will continue at rest. But it also means that if they're moving, they will continue moving. And the important part is with a constant velocity. In order for something to have a constant velocity, it requires two things. What would constant velocity require? Same speed and same direction. Okay? Constant force is something different. So, inertia. Things continue doing what they're currently doing. They either want to stay still or they want to continue moving with that constant velocity. All right, a few more terms that go along with these, and that's the gist of Newton's first law. And if you look on the board, look on the wall, we're at Newton's first law, one word, inertia. There it is.
Why did they come up with that word? You know what I mean? Like, why is it inertia?
I mean, it's inert, and inert is something that doesn't change. So I'm assuming it's derived.
So when somebody's like, oh, it's inertia, that means they're talking about, oh, it's first law.
Pretty much, yeah.
Yeah.
And we talked about that, like, you know, Newton's first law gets applied in certain situations. Like, okay, if something is sitting still, it just sits there. It doesn't do anything unless we make it. But we talked about the idea that something moving will also continue moving. I think we talked about, like, things in a car when you slam on the brakes, right? Loose stuff that's in the seat. If you apply the brakes, that stops the car. The seatbelt stops you. But if there's nothing holding papers or notebook or whatever, right, it just keeps going, and that's why it flies forward. Not so much that it flies forward, it just keeps doing what it was doing, and everything else stops.
But then it stops it because it hits something.
Right, it won't stop until it hits something, and that just happens to be in front of the car.
Right.
Here, go ahead. Okay, with a baby car seat, when babies are really young, their neck muscles aren't really supported. You have to hold their head. So when you have a young baby, the car seat is supposed to be backwards for the first year of their life, because now if they're in their car seat, generally you worry about when stopping real quick. And when you stop real quick, you have this tendency to go like this. But if the baby is backwards, now the back of the seat is supporting their head. So if you have to stop real quick, their head wants to keep going, but it runs into the back of their seat. So they don't end up doing that. And then you get
so that the babies are like...
Yes, because babies' neck muscles aren't strong enough. What? Possible. I mean, Allison, that would be no different than you shaking a baby. It's basically the same thing.
A baby kid.
Okay.
A baby kid.
Please don't say baby.
You should see the kids I babysit. It's kind of touching.
Sam, this is being recorded, by the way. So,
It's Dylan's cousin.
yes.
So if they're sitting back and you start really fast,
Same thing, yeah. Although so hey, you guys are already pretty behind. So you guys stay on track. Chris, the same idea would apply, although the acceleration that occurs in stopping is much greater than the acceleration that can occur from starting. Okay. Now, the one thing that could happen would be the idea if somebody hits you from behind, okay, because that would be a problem where the car jerks forward, but the baby like does this. You know, it's kind of you try and prevent the most likely thing from occurring, and that's generally the stopping effects. Okay, that could happen as well, although not quite as likely. So, okay. Go.
If the object were to stop, like the car were to stop, but you're still going, are you gonna be going the same speed as the car?
When you're traveling, you are. Like when you're riding in a car and it's going 35, you're going 35. That ends up no. So yeah, you would continue going 35 until something makes you slow down. That being the seatbelt. So the seatbelt basically causes the same acceleration on you as the brakes cause on the car. So you now you do lean forward a little bit, right? So it's not quite as much acceleration because they're different. You're still going forward because the car is slowing down a little bit more than you're slowing down. So it makes it appear that you're going forward. Does that make sense?
Like the object will like keep going the same velocity.
Because Newton's first law says, right? Rest remains at rest. Motion continues in motion with a constant velocity. So yes, if you're going 35 and that car slams on the brakes, you're going to continue to go 35. Now, the fact that like that because you're sitting on the seat, there's some friction there between your pants and the seat, so it probably won't be exactly 35, but that idea, yes. All right, next topic that goes along with this idea of Newton's first law is mass. Okay? I'm assuming you guys, we talked about mass in this class, and mass is defined as a measure of how much matter that makes something up, and that is true. But from an inertia standpoint, from a physics standpoint, okay, mass will also tell you how much inertia something has, or something's ability to maintain its current state of motion. Example, you're sitting in a car that is sitting next to a big semi-truck at a stoplight. Light turns green, you hit the gas, semi-truck hits the gas. What generally happens? You go quicker than the semi-truck, right? Because if you look from a mass standpoint, right, it's easier to get you to start moving than it is to get the truck to start moving. You have less mass, you have less inertia. But inertia is a two-way street, right? It's harder to get that truck to start moving, but it's also harder to get the truck to do what? Stop moving. If you're on the highway and you're in front of a truck, right, and you both slam on your brakes at the same time, you're going to get hit because the truck is harder to stop. It takes longer for that truck to stop than it does for you because it has more inertia.
Is that why when it's going like down a hill, you have to be like, they are all like, be careful.
Yes.
Because
Yes.
you can't like.
But Sam, it also says too that like on trucks, there's all those stickers on the back, and one of them is one of them basically tells you don't go right in front of the truck. You need to be a good distance ahead because the truck knows that it takes a while for that truck to stop because right, more mass something has, it's the harder to change its motion. It's harder to get that big heavy object to start moving, but it's also harder to get it to stop moving. Okay? I mean, if you think about it in terms of just like different objects, right? If you throw a baseball or a softball or something, right, versus rolling a bowling ball, okay, it's easier for you to throw the baseball or the softball than it is to roll the bowling ball, right? But try catching a bowling ball, right? I mean, it's a lot harder to do because it has more inertia. it's already moving, it wants to keep moving. Good there? Okay. Next concept. Next concept is net force. Okay. We symbolize net force in two separate ways, depending on what book you're reading, blah, 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 blah. So the first thing we'll do is we just do F with the subscript net, okay? Or we will use this funny Greek symbol, okay? It looks like a sideways F. It is not an E, okay? Don't write an E. What? So there are some fraternity sororities that have one of those in their name. It is a Greek letter. It is a Greek letter sigma. That's actually a capital sigma. Okay? Greek letters come in uppercase and lowercase, just like English language or Arabic, I guess. What? The lowercase one looks kind of like this.
I can't draw sigmas for my life.
No, we use Arabic numbers. Anyway, so, but just like we come across other things like delta, whenever you see delta in front of something, that tells you to do something, right? What do we use delta to represent? Change. Sigma also represents something. Sigma is a summation function, right? Which means mathematically, what are we going to do? We're going to add. Okay? So whenever we see sigma something, that means add them together. Okay? As far as net force goes, net force is defined. Net force is the combined effect of more than one force acting on an object. We talk about that forces cause acceleration, but very rarely is there a situation where a single force is affecting the motion of an object. When that's the case, when there's more than one force acting on an object, we have to look at the net force, or the combined effect of all of those forces, which, because it's a summation function, right, is a sum of all of those forces. Okay? Good, go ahead.
I don't think it's like sum instead of
That's, I mean, if you do plus, 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 it's basically the same thing. Right? It's just a shorthand way of writing it. Like whenever we have delta, that always means final minus initial. But instead of writing final minus initial every time, we just write delta something. Same thing.
On the computer, you're doing Excel, and then you want to do like a graph, remember?
Yes.
So you do that. There's like a little thing, and
Yeah.
you press sum.
Yes. Now, what does that mean? From a Newton's first law standpoint, the motion of an object is only going to change if the net force is not equal to 0. For example, there's the remote to the projector sitting on the desk. Right? Is it moving? No. And inertia says it's not moving now. What is it going to continue to do or not do? It's going to continue to not move. Okay? However, are there forces acting on this remote? Yes. Mainly, what's the big force we can't get rid of? So gravity, right? But is that object falling down because of the gravitational effect on it? It's not. Because the desk is pushing up, right? Sam, how hard is the desk pushing up compared to how hard gravity is pulling down?
Like the same.
It's the same, right? So that means that the combined effect of those two forces is what? 0. Okay? When we calculate the net force acting on something, there we go. So, calculating net force, it's a summation function, right? It's adding things together. But forces are vector quantities, meaning that forces have to tell us what? Direction and magnitude. In one dimension, how many choices do we have as far as direction goes? You just got 2, right? You can either go this way, or you can go this way. And how do we, in one dimension, okay? In one dimension. Okay? And how do we distinguish this way from that way? We call one positive, we call one negative. So if two forces are in the same direction, what sign do they have? Or well, they both have the same sign, right? Okay. But if they're in opposite directions, then they have different signs, right? So if you have forces that are in the same direction, essentially what are you going to do? Add. If it's two positive numbers, you get a bigger positive number. If it's two negative numbers, what do you get? A bigger negative number. But as we've discussed, is a bigger negative number small? It's just big, but in that direction, right? But if they're in opposite directions, right? Technically, what are you still doing? You're still adding. But if you add a positive number and a negative number, mathematically, what is that equivalent? Subtract. Well, it's 0 if they're both what? But they're going different directions equal. Okay? Good.
Wait, like you said that the desk is pushing up.
Yes.
Is that
The desk is applying a force to this object by the fact that it's touching it. Okay? So, does the ball accelerate when it hits the desk? Because first it slows down, then it changes directions, then it speeds back up in the opposite direction. That's all acceleration, right? I caught it. But in order for that to happen, there has to be a force there, right? So the fact that this thing is touching that object, it allows it to apply a force to cause the motion of that object to change.
does anything like sitting on an object have? Is it like falling and being knocked with gravity? I think of this happening.
Generally, if what is true about that object, Caroline, is your seat applying force to you now? Yes. How do I know that your seat is applying a force to you? Because you're not falling, right? So if that object is not moving, then yes, it's the same as gravity. Okay? Now, if I do something like this, okay, right? Where this, I make this go faster on the way down. Okay? Gravity is still acting on it. And I'm acting on it upwards, but are we acting the same? Right. Here. Okay. Ready? Okay. Does that make sense?
Yeah.
That ball only has gravity acting on it, right? So if we talk about it from this standpoint, the net force on that object, there's only one force acting on it. The net force is just that force. Here, this ball has two forces acting on it. Gravity downward, me upward. But gravity is obviously stronger than my upward force because of the fact that what's this object doing? It's still going down, but more importantly, it's going down and what's happening to it as it's going down. It's accelerating, right? Okay. Now, if I do this, okay, at the very beginning, I'm going to ease up on the ball and cause it to start going down, okay? But now, as it's moving downward, right, what do we see about how fast that object is going downward? It's going slow, but Allison, it's not doing what? It's not accelerating. It's trying not to make it accelerate, okay? Are there two forces acting on this ball now? Yes. Still gravity in my hand. And what can we say about those two forces?
They're similar, but your hand is a little less.
Okay. At the very, very beginning, my hand is a little less. But now, when it's moving at a constant velocity, right, what has to be true about objects with constant velocity? We talked about this before. That force is zero. Does that make sense? So we can have balance, we can have this net force being zero for an object at rest, like that, and also for an object moving. Okay, right? Tug of war. Because basically what we were just talking about. That here, forces acting out are balanced, same magnitude, opposite direction. The net force is zero and there's no change in the motion, right? The rope in this tug of war started at rest, so it continues at rest, right? But now, if let's say the people on the yellow side walk backwards and the people on the blue side walk forwards while still pulling, right? That rope would just move with a constant velocity, right? Now, granted, to get it to move to the right, the people in the yellow would have to pull stronger, at least for a little bit. But once it's already moving, if we balance those forces out, it just keeps going. Does that make sense? If they want to do what? Well, yeah, if they want. Wait, I'm just saying, hypothetically speaking, okay? If we started them moving, right, and then once they're already moving, if the two forces balance, now it just keeps going. Okay. Does that make sense? We refer to this situation as equilibrium. Equilibrium, by definition, is when the net force of something is equal to 0. But, as we just discussed, like feed into this slide, equilibrium can actually look two ways. What does equilibrium look like physically? What's one way it can look? Stop, right? This object here at rest is in equilibrium. Okay? But the other way it can look is what? It's moving with a constant velocity. Because in both of those situations, the acceleration is equal to 0. No. But same thing you could do. Have you ever seen
This vacuum chamber.
Yeah, if you have vacuum chamber is not 0 gravity. It's actually got gravity, but it has nothing else. Sam, have you ever seen those things where people who skydive sometimes they like train and there's a big huge fan in the floor?
Yeah.
Okay. That is a situation where you're going to be in equilibrium because gravity is still pulling down on you, but now there's so much wind pushing up on you that you can just float. Now it's not perfect equilibrium, so they fall down and stuff like that, but that's a situation where we're trying to create equilibrium.
But I wanna it seems so much fun being in 0 gravity. I don't wanna go
So
in space.
now what we refer to as 0 gravity is a little bit different than actually 0 gravity. So we'll get into that a little bit more tomorrow.
Mr. Planets
I still wanna go.
I know. All right. So that wraps up Newton's first law. Inertia, mass, equilibrium. These are all things related to Newton's first law. Let's move on here to Newton's second law. Because it's really not that complicated. But applying it to situations is where the difficulty is. Yes, that's our lab. All right, so Newton's second law. Newton's second law is kind of wordy, but it's summed up in a nice, tidy equation. So first, Newton's second law. Newton's first law deals with inertia. Sorry, hold on a second. Before you start writing. Okay, so Newton's first law deals with inertia. And inertia is things doing what? No. Inertia is things staying the same. Could be moving, could be not moving. Newton's first law deals with things staying the same. Newton's second law deals with things changing. So that means, Nick, Newton's second law is going to deal with what? Acceleration. Very good, Nick. Well done. So, Newton's second law talks about acceleration. Acceleration is affected by two things. Acceleration is affected by the net force acting on the object and the mass of that object. So there are two factors that will affect the acceleration that an object experiences. One is its net force, or the net force on it, and the other one is the mass of that object. So Newton's second law summarizes these ideas in a nice tidy equation. There it is. So sigma F, or if you want to write it this way, F net is equal to m times a. So net force is equal to mass times acceleration. Now, we can rearrange that equation and get acceleration by itself on one side of the equation. If when you write it this way, when you write the fraction, write it actually as a fraction and put f net on the top and put f on the bottom. It'll be a little easier to see what I'm going to tell you next. Go ahead. So write it this way. That's why I picked it. Like that. All right. So let's take a look at this equation. Okay. First, where is m in this fraction? It's on the bottom, right? It's in the denominator. If m gets bigger, what's going to happen to the accelerations? What kind of relationship between mass and acceleration? Inverse relationship. In this fraction as well, F net is in the numerator. Net force in the numerator. If it gets bigger, acceleration gets bigger. Nick, what kind of relationship? Direct relationship. Good. All right, so we said acceleration is affected by two things. Acceleration is directly related to the net force acting on an object. So if the net force increases, the acceleration increases. And as the net force decreases, acceleration decreases. You can probably think of it this way, right? If you throw something, if you throw it lightly, how much does its velocity change? Not a whole lot. If you throw it harder, how much does its velocity change? A lot more. Uber. Like carry away.
I love Uber.
But then on the other side, right? Acceleration inversely related to the mass. As the mass increases, acceleration decreases. As the mass decreases, acceleration increases. That would be the example of you and the semi-truck sitting there at the green light, right? If we applied the same force to both of you, which one's going to take off faster? Which one's going to move faster? The car, because the mass is less. Okay. To wrap this up, I want to discuss your graphs from the lab. If you have them, it might be good if you can pull them out. That's what we generally talk about. Okay. You had to make two graphs based off of your data from the lab last Wednesday. The first graph you had to make was force versus acceleration. What kind of relationship did we just say force and acceleration have?
Direct.
A direct relationship. So what should this look like on your graph? A straight line. It should be upward sloping, but it should be a straight line. Acceleration and mass have what kind of relationship? Inverse. Do you remember what the inverse equation or inverse graph looks like? It's kind of a parabola, but it's not exactly a parabola. It like starts high and goes low. Right? Allison, go ahead. Actually, there's space on your lab, I think, for the question. Yeah. Right on the lab. If I give you space, you can right there. So, that's what you should be looking for as far as your graphs are concerned. Okay? If they don't match exactly, it's okay. Alright? But if they're generally in that shape, that's what we're looking for. Okay. So, at this point in time, hold on. One more minute. At this point in time, you have enough information to make your graphs. You could have made your graphs before now. But then you also have information that you need to answer the questions based on the lab. Okay? It is due tomorrow, but if you have questions about them, we can talk about them. We can discuss them at the beginning of class tomorrow. Okay? Good? All right. We do have black tomorrow, yes.
For next year.